In the previous video, I introduced the concept of reduction of order for second-order linear homogeneous differential equations. In this method, what we do is that if we have a known solution y1, we try to find this factor v that we multiply y1 by in order to find the second linearly independent solution, which will give us the general solution for the differential equation. So here we're going to tackle an example. We are given a second-order linear differential equation. And recall it is linear because we have no nonlinear functions of y, such as sine of y or the derivative of y raised to a certain power or something like that. We're also given that y1 being equal to x is a known solution to this differential equation. So what we're going to do is that we're going to try to apply reduction of order to this second order ODE. Now recall that when we derived our solution for v, we started from a general form such as this one. And this is the general form that you will want to convert your ODE to before you start solving your ODE. And this general form has a 1 in front of the highest order derivative y double prime. So for us to cast this differential equation into standard form, we need to divide by x squared. So doing so gives us y double prime plus 2 over x y prime minus 2 over x squared multiplied by y, all of this being equal to 0. So this is what we call standard form. So you start from this point before you start doing your reduction of order. So what we're doing is that we're seeking that second linearly independent solution, and for us to do that we need to find this factor v, which from the previous video is equal to this integral over here. So we are given this y1, which we'll use in this integrand over here. And now let's be clear about our terms. So here again is p of x, this is q of x, and this is r of x. So let's go ahead and try to find v. So v of x is equal to the integral of 1 over y1 squared. So y1 is given to us as x, so this will be x squared. This is multiplied by e to the power of negative of the integral of p of x. Now p of x is equal to 2 over x. So let's try to simplify this before we tackle the integration. So we have 1 over x squared, and what we're going to do is that we're going to take this 2 out of the integral. So we have e to the negative 2, and then we have the integral of 1 over x, which is equal to ln of x, and all of this dx. So we're going to continue up here. We're going to further simplify this by using our rules for logarithms. So as you remember, you can take this factor here and bring it as an exponent in the logarithm. So this allows us to write e to the power of ln of x to the negative 2. And so all of this here, again, from your rules for exponents and logarithms, will just be equal to x to the negative 2. So now we have the integral of x to the negative 2 divided by x squared dx. So this is equal to the integral of 1 over x to the power 4 dx, and that is equal to minus 1 over 3 x to the minus 3. So this is our solution for v. So y2 will be equal to some constant c multiplied by v multiplied by y1. So we can write c multiplied by negative 1 over 3 x to the negative 3, and then all of this multiplied by y1, which is equal to x. Now notice that this minus 1 over 3 is just a constant, so we can simply just absorb it into the constant c. So our y2 is just equal to c multiplied by x to the negative 2. This gives us the general solution for the ODE, that is equal to y is equal to c1 y1 plus c2 y2. And we now know what y1 and y2 are. So c1x plus c2 over x squared. So this is the general solution of our second order linear homogeneous differential equation obtained by reduction of order, given that we were told that one of the two solutions to this ODE was equal to x.